Yeah, so the chapter here is going to be shorter than it would have normally been, but I want to start with the first section, which is differential equations. Which I think is one of the most interesting ones that you're going to see. There's also, it's the one that's the most relevant right now. Plus, we have already started doing some of the work for this section. Okay, so I'm going to start with this. I'm going to present some of the material today. You're going to have to do some practice problems, and then that's pretty much where I'm going to stop for the day. So let me start the piece. Differential equations. We have already talked about differential equations before in the class. We talked about, finding equations for derivatives of functions, but we haven't really talked that much about how to model processes and so on. So that's what we're going to be focusing on today. Now, why do we care about differential equations? So sometimes it is easier to describe why a quantity is changing, right, than it is to explain why a quantity has a given value at a given time, right? So then it is to explain why a quantity has a given value at a given time, right? So what this means is simply that sometimes we want to express how quantities are determined, and in a lot of situations you're going to have that when you're trying to model what the value of quantity is, it's not necessarily going to be as easy to model the actual quantity, but it's going to be a little bit easier to model how the quantity is changing. So why is it increasing? Why is it decreasing? And why is it increasing this much? Or why is it decreasing this much, right? So the idea today is to figure out how do we model how a quantity is changing. So if you think about an easy example, so for example, if you have the population of a city, it's easier to explain why the population of a city is growing and by how much than it is to explain why the population of a city is this amount at this specific time and why tomorrow it's this amount at that specific time, and so on and so forth, right? So it's easier to explain why the population of a city is growing than to explain why the population at a given time has a given value, right? Does everybody follow this? Yeah, so like it's just, yeah. Okay, good. So now what that means is, okay, so this same argument applies to a bunch of other quantities, and our idea is to say, okay, now mathematically speaking, if I have a problem that helps me formulate how a city is growing or how a given quantity is changing, is it possible for me to determine what the actual value of that quantity is going to be at a given time? Right, so let's translate that in terms of math. So in terms of math, here's the problem that I'm trying to solve. If I can properly describe how a quantity is changing, can I determine what the quantity will be sometime in the future? Right, so this is the idea of the problems that we're going to formulate today. And this is something that makes sense because imagine that I don't know, you're the mayor of the city and you know how your population is growing or how your population is decreasing. So you know why your population is increasing, why your population is decreasing. A fair question to ask is, okay, if I know this, is it possible for me to guess what the population of the city will be a year from now? or 2 years from now. And that way, if I can predict the population 1 or 2 years from now, then I can make appropriate decisions in order to handle the population that I'm going to have a couple of years from now. All right, so that's kind of the idea here. Now, of course, this is still just a sentence. We haven't translated anything into math. And so that's what I'm going to do right now. So this is the problem that I've formulated in terms of what I want to do philosophically. And now I'm going to try to translate this into an actual mathematical problem. Yeah. So the first thing is that I'm talking about a quantity, right? So I'm talking about a quantity that might be changing, but the quantity is changing with respect to time, right? So that means that this quantity, I can interpret it as being a function. Does everybody understand that?
Yep.
Okay, so this is a function of time. And then, so same thing over here, I have a function of time. Now, if I have the word changing, so if I'm looking at the change of a function, do I have a mathematical tool that allows me to describe that?
Derivative?
A derivative, right? So if I have the word change, so the rate of change is given by the derivative, right? So I have the derivative over here. And then the last thing that I have is sometime in the future. So that just means that I'm guessing, okay, so t, so sometimes is some value of t. And I'm just going to put in the future in brackets here, okay? So essentially what we've done is looked at our statement and identified the terms that actually can be expressed in terms of math. And what that allows me to do is to reformulate my problem into a problem that can be solved mathematically. Okay. So if I think about this problem now, what I'm essentially saying is, all right, if I can properly express the derivative of a function, right, which is equivalent to saying, if I can properly describe how a quantity is changing, so these two things are the same, just that this is in terms of math, then my question is, can I determine the quantity of the function? So can I determine the value of the function at a given t that is in the future? So is it possible to find the value of the function for some value of t? Now, I'm not specifying which value of t, I'm just saying sometime in the future. And so I'm going to say, is it possible for me to find the value of the function for any value of t? Okay, and so this is the problem that we're going to start working on today. Do I have any questions, or is this clear for now? All right, so the idea here is going to be to first work on what it means to actually express the derivative of a function. And then once I've tried to explain how to model the derivative of a function, we'll see if we can actually solve this problem. Okay, so there's going to be several parts. We're not going to get to the end of this today. This is a lot harder than it looks. So we're going to just work our way up. So we're going to start by looking at a problem that we do know how to solve. Okay, so let's start with a case that we know how to solve. Okay, so this is the first one. And this is with an example that relies on things that we've already seen before in the class. So this is an example which is the following. So suppose that the population, or the number of students, of John Abbott College is increasing by 40 students per year. Okay, this is not actual data, it's just for the sake of the example. It's increasing by 40 students per year. And in 2019, the population was of 7,000 students. All right, so this is a problem that we have initially. Have the population of students is increasing by 40 students per year, and in 2019 the population was 7,000 students. So the idea here is going to be to start modeling this problem, and then we're going to see that this is a problem that we can actually solve, but it should give us some intuition on how to start modeling things. So the first thing that I need to do is to describe what my time is and what the units for that time are going to be. And the second thing that I'm going to ask and that we're going to have is the second quantity, which is the population that depends on the time. So the number of students as a function of the time, right? So I have that. My variables are going to be t, which is time. And because this is written in number of students per year, I'm going to say that t is time expressed in years. And then I'm going to write down a function, or I'm just going to denote the population of students. So maybe I'll denote it by P for population, is the population of students at time t. At time t. All right. Yeah. So that means that P is a variable, which is the population of students at time t, but because it's given by t, this is the dependent variable, and so it can also be expressed as a function of t. Okay, so this is what we call, this one over here is what we call the independent variable, because time just happens on its own, and then P is called the dependent variable because it depends on the time that you're looking at. All right. So this is the information, this is just how I'm naming my variables. And now what I'm going to do is try to actually model the information that is given in this problem. So I'm going to start by modeling this part of the problem, which is to say the population of the students is increasing by 40 students per year. So what this is telling me is that if I were to look at how much my population, so at the change of the population within a year, I would get that that result is equal to 40, right? So that means the population of students, so P, has a rate of change, so has a rate of change or a derivative that is equal to 40. And 40 is positive because the population is increasing by 40 students. If the population were decreasing by 40 students, then it would be negative 40. If you're too shy to put your voice on, to unmute your mic, and you want to ask a question, you can write through the chat. I'll also answer questions there. So please don't be shy. It's a lot easier for me, again, to gauge where you're at if you ask questions. Okay, so I have that the population of students is increasing by 40 students per year. That means the derivative is equal to 40, or I can rewrite this as dp over dt is equal to 40, right? So those, like, these two things are equivalent to one another. So far so good. Can everybody that understands please raise their hand? Go. All right, so far so good. That's nice. So now what we said is at the beginning of the semester, we said, okay, well, actually, if I do integration, I know that I can recover the original function from the derivative. So if I want to just know what the population is at any given time, then what I'm going to do is integrate this, right? So I knew that P of t is equal to the integral of P prime of t dt. And that means that my population would have been the integral of 40 with respect to t. And if I try to evaluate that, I know that this gives me 40 times t, because the integral of just a constant is going to be 40, the constant times the variable. And then I'm going to have plus c. Okay. So this is the first thing, which tells me if you want to solve a differential equation, there's going to be some integration involved. Okay, so this is the differential equation because it tells me the derivative as a function of something. All right, so now we know what the original function was, except we don't know exactly what the original function was, right? Because now I have this value of c over here. And what we said at the beginning of the semester is that the reason why we have the value of c over there is that I only know the derivative, so I only know how my function is changing. But depending on where my function started, I'm going to have a different specific function that is going to pass through that point. So what I'm going to need is something else. Does anybody remember what I said I would need in addition to the differential equation if I wanted to find my unique solution?
The initial condition.
An initial condition, right? So I need an initial condition, which in this case has also been given, right? So I have in 2019, the population was 7,000 students, right? So what that means is I have the population at a given time. I just have to make sure that I write this down as a proper, that I make sure that 2019 corresponds to a specific value of t. So what I'm going to say here is that t equals 0 corresponds to 2019. Okay. Now you don't necessarily have to make it correspond to 2019, but you can make it you can say, for example, t is equal to 0 is the year 2000. Or t is equal to 0 is actually the year 0. And depending on the value that you make the correspondence with, then you're going to have that the function is going to be given in terms of a different variable. So if you wanted to look at 2020, for example, with my definition, that would be year 1, but with the definition that starts at 2000, that would be t is equal to 20. So it just depends on what value you choose. So initial condition, in this case for me, is that p of 0 is equal to c. And that means that now I can solve this equation. I can plug 0 into my expression for p of t. So that means that 40 times 0 plus c, whoops, this is not equal to c. I mean, it is equal to c, but this is not what I wanted to write. My initial condition was that p of 0 was equal to 7,000. And what that means is that 40 times 0 plus c is equal to 7,000, which means that c is equal to 7,000. And so if I want the full expression for p of t, that's going to be 40 times t plus 7,000. Okay, so can I see a show of hands for those of you who understand everything that I've done so far? Okay, so I think all hands are up. Okay, there's a couple of people. Okay. Okay, so Julien Lemieux asks, is the initial year 2019 or 2020? So what I'm saying here is t is equal to 0 corresponds to 2019, which means that p at 2019, which is at t is equal to 0, is equal to 7,000. right? Because that's the population that we have. In 2019, you have that the population is 7,000 students, which means that at time 0, the population is equal to 7,000. Is that okay, Juliette? For anybody else that didn't understand that part? Yeah, okay, good. All right, do I have any questions about this? Because things are going to get complicated. Yes, what's up?
I have a question.
Yep.
So the P0 equals 7,000 just to find the initial.
So that's the initial condition, and then that allows me to find the particular solution, right? So remember, we talked about at the beginning of the semester, we talked about how when I have the derivative of a function, I can only find, so for example, here I had that the derivative was equal to 40. So that means that the solution could be this function where the slope is 40, or it could be this function where the slope is 40. It could be this function where the slope is 40 for everything that way, right?
Oh, yeah, yeah.
But if I want the specific solution that is going to pass through a given point, then I'm going to have to fix that point, and then I can find the actual solution that passes through that point. Whoops. Well, you get it.
Yeah.
So, it would be the specific solution that passes through that point and whose derivative is equal to 40. All right, does that make sense?
Makes sense.
So what I'm trying to do is fix that initial point. Okay?
Yep.
Any questions? Anyone? Is everyone okay with all of this? Yeah.
All good.
All right, good. So next thing. Okay, so this is a very easy differential equation to solve. The integration was super easy to evaluate over here. But more importantly, the derivative was actually just a function of t, right? So I was able to integrate it. Now that's not necessarily the case. And here I'm going to start complicating things quite a bit. So as soon as you get lost, you need to either raise your hand. I'll be keeping track of anybody that has their hands up, or to ask a question through the chat, because things are going to get a little bit tricky. All right, Radu, you have your hand up. You can lower your hand, please, unless you have an actual question. Okay, thank you. All right, so the first example that we're going to look at today, the first complicated example that we're going to look at today, is something that we call unrestricted growth. And unrestricted growth is a model that is very frequently used to model certain populations under ideal conditions. Okay, so one model for the growth, one model for the growth of a population, is that the population grows at a rate proportional to the size of the population. Okay, so I'm going to ask you to copy this, and then I'm going to expand a little bit on this. Okay, so what we have is the possibility that a population is growing at a rate that is proportional to the size of the population. So why would this be a suitable model? Well, you can imagine that a population is going to grow at a certain rate. So for example, if you have a population of animals, this population of animals is going to reproduce at a given rate. And then if they are doing pretty well, if there's enough resources, if there's enough space, then their offspring is going to be a little bit larger than the original population, right? And once that population is a little bit larger, there's going to be more animals that will be able to reproduce with one another, right? And so the subsequent offspring is going to be even larger. And you can keep thinking about it step after step, right? So what that means is that as the population of animals is growing, you can consider that the rate or the rate at which the population will be growing is also going to be larger, right? So the more animals that I have, the faster they're going to reproduce. Does everybody understand that? Can I see a show of hands for those of you who understand that? Okay, so the idea here, I'm going to write it down, is the more animals there are, the faster they will reproduce. Okay, so most people raise their hand. That's good. Now I put animals in brackets because it's not necessarily just animals. This model is also pretty good for modeling bacteria and stuff like that. So yeah, so it's not necessarily just animals. It can be any type of population, but the example with animals I think is fairly intuitive. So under which conditions is this a reasonable model? So this is a reasonable assumption for bacteria and animal populations under ideal conditions. Under ideal conditions. Now, what does ideal conditions mean? It means that they have an unlimited environment. So unlimited environment means that they have unlimited space, unlimited food, unlimited resources in general. They also have adequate nutrition. So that means they not only have unlimited food, but they have the right food at their disposal. There's the absence of predators, and so on and so forth. Okay. So these are conditions that you can have. And so once again, I need to define my variables, right? So that means I'm going to have that t, as before, is going to be the time, which we said was the independent variable. And here again, I'm going to denote by p, which is going to be a function of time, the population or the number of individuals at time t. All right. Juliet, you have your hand up. Is that just because you forgot? Okay. All right, so now I have a notation for the size of the population. I have a notation for the time. Now what I'm going to try to do is to express what this assumption means. And what that's telling me is the population is growing, so p prime of t. So that means population grows means rate of change. It means rate at which it's growing means rate of change, so that means derivative, right? So the population grows means the derivative, the rate of change is proportional. So it's proportional means there's some number, which I'm going to denote by k, times the size of the population, right? So it's the size of the population multiplied by some constant. So it's proportional to the size of the population, which is p of t. Okay? Does everybody understand this part?
Mm-hmm.
Everyone in the okay, I don't have questions in the chat either. Yes, Xiaoshen. You understand?
Yeah, miss.
Yeah, okay, good.
What's K?
K is just some constant of proportionality. Okay, so this is some number.
Okay, thank you.
Okay, we don't know. So K is the constant of proportionality. Of proportionality. that clear for everybody? Right. So what K represents is basically the rate at which the population is growing. Okay, and so what I'm going to do now is just to look at what happens for different values of K, right? So we have maybe something like this, and then something like that. I'm going to look at 3 possible values, and that will be that for this part. Okay. So the first possibility is that K, is that K is equal to 1. Okay, so that just means that the population is growing, so the derivative is equal to the function itself, right? So P prime of T is equal to, oops, I think I'm writing too small, P of T. Right, so at this point, I'm just going to look at one possible case. Okay, so suppose that I start with a population that is equal to maybe this amount. Okay. If this is my population and the derivative is equal to the population itself, that means that over here, let's say this value is about 0.1. My derivative should be equal to 0.1. Okay, so be really attentive over here. And if you have any questions, again, ask me. Okay, so what I have here is that my population at time 0 has a given value. And so this is time and it has a given value. Now, the derivative at that point has to be equal to the value of the function itself, because this is going to be equal to the number of elements that are initially available. Now, if this is 0.1, that means that the derivative is going to be 0.1, and so after 1 unit, I'm going to be moving just this amount up. So maybe the derivative over here is going to be like that. Is everyone okay with that? More or less?
Mm-hmm. Yeah.
Now, after I get to this point, my population will have grown a little bit, right? And when I look at the derivative at this point, that's going to have increased a little bit more like this, right? So my derivative itself is going to be a little larger, right? So my population is going to be growing a little faster. And then if I look at the next point, again, my population is now larger, and so my derivative will be larger as well. So I'll have something that might look like that. And then if I keep going, the larger my population gets, the faster my population is going to grow. And so I'm going to have something that looks like that. Does everybody understand this?
Mm-hmm.
Do I have any questions from the chat? No. Why it doesn't start at 0, 0? That's just an arbitrary choice. So it could start at 0, 0. It could start at 1. Here I've just chosen it to start at a small value so that we can see how it evolves over time. But it could start at any possible value, right? So it could start at 0, 0. The problem is that if it starts at 0, then that means that my population is 0 initially. So of course my population isn't going to grow, right? Because if I have 0 animals to begin with, then I shouldn't have any animals afterward because I don't have any animals to start with. Does that make sense, Radu? Right. So the only thing that I want to make sure of is that it starts just a little bit above 0, so that I can see how my population is going to grow from just a couple initial individuals. All right. So this is the case when k is equal to 1. Then I can say, okay, well, what happens if my rate over here is actually a little smaller? So what happens if k is equal to 1/2? Right? So then my derivative is going to be equal to 1/2 of the value of my function. Right? So I'm going to have something like this and like that. And so what that's going to mean is that if I start again at some small value, then my derivative here is going to be, again, proportional to this, but it's just going to be 1/2 of this. So that means that I'm only going to move this amount, but in 2 units to the right. So that means I'm going to have something that looks like that. And then I'm still going to have moved to the right, but I will have that the new derivative over here is a little bit smaller than the new derivative that I found over here, right? So it's going to be maybe like this. And then if I keep tracking over here, my derivative is growing slower. And so this is going to look like that. Does everybody understand this? Do I have any questions from the chat, from the participants, raised hands or anything? Can I see a show of hands for those of you who understand what I'm doing? Good, okay. And finally, if I have that k is equal to 2, that means the rate of change is larger. That means that the derivative is going to be equal to 2 times, oops, is equal to 2 times p of t. So 2 times the population. So if I have something like here, then my my function is going to grow. Okay, so I have Galen, Vicente, Sarah, and Juliet still with their hands up. Unless you have a question, can you please take them there? There you go. So over here, again, I'm going to move a little bit faster. So that means I'm going to move maybe like here. And then my derivative is going to be a little bit larger, right? Because now it's 2 times the size of the population. So maybe I'll end up, oops, with something like that. Okay. So what this is telling me is that the constant of proportionality that I have over here, this term that looks like it's not that important, we don't really know what it is, it's actually determining how fast my population is growing, right? So if k is really large, then my population is growing really fast. Whereas if k is really small, then my population is growing, but it's growing at a much smaller rate. Yes, Galen, there's a question?
Yeah. So what if k is negative?
If k is that's a great question. So if k is negative, then we're going to have a population that decreases, right? Because if k is negative, that means that the derivative is negative, and that means that the population would be decreasing. So we're going to look at this case in a little bit, but for now we're just going to look at the case where k is negative, is positive itself. Okay, but if it's negative, you can think about exactly the same thing. Actually, maybe I'll do the example here on the side. So I'm doing it in red just because it's a bit different. If you start with a given value at the beginning, let's say this is 1, 2, and 1 and 2, and you have that k is equal to -1, then that means that the derivative is equal to negative times p of t. And so that means, for example, if I start here, now here I'm going to start larger just so that I can track things a little bit better. That means that over here, my derivative should be -2, right? So it should have a slope, like my line should go like this. And so for a little bit, my derivative is going to be like that. Okay? And then at this point, my derivative is going to be minus whatever this value is. So it's going to be almost -2, but maybe a little bit larger. So it's going to get a little bit shallower like that, right? And then at this point, it's going to be even like that. And then if you keep tracking this, you're going to have something that goes like this. Does that make sense?
Yeah.
All right. And you see, for example, in this case, the closer you get to 0, so your function is going to start decreasing like this, but the closer you get to 0, the closer the derivative is going to get to 0. And so the slower your population is going to start to decrease.
Is it going to touch 0?
It's never going to touch 0 because as you get closer to 0, the derivative itself gets closer to 0. And when the derivative itself gets closer to 0, what that tells you is that the change is smaller and smaller and smaller, right? So it's going to start decreasing less and less and less and less until it reaches an asymptote like that. Does that make sense?
Yep.
Okay. Is everybody okay with this? Yeah, can I see a show of hands for those of you who understand what I've been doing on the board? Good, okay. All right, you're gonna see this is going to get interesting right after. So All right, so we have that model. Now, of course, this is not necessarily a model that is easy to solve for, because you have, for example, if I think about this model over here, oops, not text draw. If I think about this equation, this differential equation that I have over here, it's not like I can just integrate this, right? Because if I try to integrate this, I'm going to have both the function and the derivative of the same function in the same equation, right? So I don't know how to deal with this yet. I'm going to learn, of course, I'm going to teach you how to deal with this type of problem, but this is not as obvious as the cases that we had before. It's not as easy as just integrating with respect to t. We're going to have to do a little bit more work. I have Sarah, Galen, and Radu with their hands up. Do I have a question?
No, I just
Okay.
forgot to.
All right, okay, good. All right, so then I'm going to talk about the second case that we're going to look at today. Just like these are the two most common examples. And then you're going to have a couple of problems in which you are going to have to create the same model. Okay, so we have restricted growth. And restricted growth is the case, oops, restricted growth. So what I said had to be an assumption for the previous example was that we needed to have unlimited resources. Now, of course, this is not necessarily the case. So for example, if you think about humans, we start growing as a population, but then, or maybe another population of animals, you start growing as a population, but then after a point, after we get to a certain number of individuals in a population, resources start to become scarce, right? So you start having not enough food, not enough space, maybe there's predators that are around or things like that. And so the population can't just keep growing and growing and growing and growing. So then what we have is, what happens if there are not unlimited resources? Okay. So instead, what if there are enough resources to sustain just M individuals in the population, where M is a constant? Okay, so what that means is that we have a number of resources. Let's say in a given forest, there's enough food so that you can sustain M, I don't know, deer. Okay, so you have enough resources for M deer. So then how is the population of deer going to evolve depending on what the initial conditions are? So once again, we have that T is the time, P is the population size. And here what's gonna happen. So the population is going to grow, grows at a rate that is jointly proportional. So jointly proportional means that it is proportional to both of the things that I'm going to say after. So it's jointly proportional to the population size. And the difference between the population size and the carrying capacity. Carrying capacity. So I'm using that fancy word now for the first time. What I mean by carrying capacity is just M, right? So carrying capacity means the capacity that a given environment has for a population. Okay? So the population grows at a rate that is jointly proportional to the population size and the difference between the population size and the carrying capacity. So if I write that fancy sentence in terms of math, what I have is the population grows at a rate, so that means derivative. The derivative of the population with respect to time, or the rate at which the population is changing with respect to time, is jointly proportional. So it's proportional. That means there's some constant k that is multiplying this, and it's jointly proportional to two things. The first thing is the population size. So first is going to be proportional to the population size, because we still should have that if there's just a few if there's just a few individuals in my population, then the more individuals you'll have, the faster they will grow, right? So that's the initial idea for that part. So if you have few elements, then the more you have, the faster they grow. But then it's also going to be proportional to the difference between the population size and the carrying capacity. So carrying capacity is the letter N, so the maximum population that you can reach. So the number of individuals that your environment can sustain. So this is going to be proportional to the difference between the number of elements that can be carried and the population size. Okay, so this is population size is P, and the difference means minus between the population size and the carrying capacity. Okay, so I'm putting a lot of emphasis on how you need to read these statements, because the first problem that you're going to have for this section in the class is to actually model the problems based on the instructions. Okay. All right, so we have this model. Does everybody understand how this model was created? If you do, please raise your hand. Does anybody think that I'm going really slow? So everybody lower your hand. And if you think that I'm going really too slow, then can you raise your hand? It's not a critique, it's just feedback. Okay, so I think the rhythm seems to be okay, because either nobody thinks I'm going too slow, or nobody thinks it's worth telling me that I'm going too slow. All right, so for the next part, I'm just going to explain a couple of things over here. The first thing, so the first thing is that you can see here that if I have a population that is close to M, so if the population, if P is close to M, so that means if the population size that I have is close to M, then this term, M minus P, is more or less, so it's almost equal to 0. Does everybody agree with that? Right? So if I have that my population size is close to the maximum that I can reach, then M minus P is almost equal to 0, because M is almost the same as P. And so that means that the rate of change, so that means that the growth, so if M, okay, no, wait a second. If M minus P over here is almost equal to 0, then that means that dP over dt, so the derivative P prime of t, is more or less to 0. It's close to 0. Right? Because 0 times something is going to be equal to 0. So that means that this thing, the derivative, would be close to 0, because this term is close to 0. Does everybody understand that?
Mm-hmm.
Yeah, okay. So if P prime of t is close to 0, then that means that the growth slows down, right? Because the growth is almost equal to 0, so that means that the rate at which the population is changing is getting close to 0 as well. So what does this mean? It means as my population gets close to the maximum size, my population is going to stop growing, because there's not enough resources for it to grow as fast. Does everybody understand that?
Mm-hmm.
Yeah, okay. So that's the first property of this equation. The closer I get to M, the closer I get to the population size, the slower I'm going to grow, right? And then if I have that my population size is larger than M, right? So if for some reason at some point, I don't know, I introduce too many animals, and it turns out that the population is larger than the maximum that I can sustain with my environment, then I'm going to have that M minus P. So P is larger than M. So if I subtract P from M, I'm going to get a result that is smaller than 0. Right? And if M minus P is smaller than 0, then that means that the derivative is also smaller than 0, right? Because if this term is equal to something negative, then I'm going to have negative times these terms, which I know are positive. And I'm going to have that the derivative over here will be negative. So what does this mean? It means that if my population exceeds the maximum, M, then my population will have to decrease because I don't have enough resources to sustain all of the elements in my population. Does everybody understand this?
Mm-hmm.
Yeah, okay. Do I have any questions about this? I'm looking at the chat, the hands raised, no? Okay. So this is like something that's really nice because it means that this very simple model is already giving me a lot of information, right? It's telling me, okay, if my population is small, make it grow, but if it gets close to M, make it slow down. So with one single equation, I'm already being able to model all of that. All right, so I'll show a little bit how this looks, and then I'm going to give you some time to work on the problem set that I already posted on Leia. So I posted something on Leia. You can go there and download it for now if you want. But I just want to give a couple of examples over here because I'm going to expand on this at the end of class. Okay, so what I have is a couple of possibilities. And then once again here, I have that my equation depends on some rate k, right? Like that's the only thing that is not fixed from the beginning. So I'm going to assume that this is my maximum. So like over here, this is my carrying capacity for each one of these equations. Yeah, so this is M and M and M. And for all of these, just for the sake of the example, again, addressing the question that Radu asked before, I'm just choosing this value just, you know, completely arbitrarily. There's no reason why I should start here. It's just for me to show some kind of case. So I'm going to assume that my population starts pretty low, right? So I only have a couple of individuals. And here I'm going to assume that this is k is equal to 1, k is equal to 1/2, and k is equal to 2. Okay, so if k is equal to 1, then as at the beginning over here, I'm going to have that my population is going to start to grow, and the larger my population gets, the more it's going to grow, right? Because the more animals I have, the faster they're going to reproduce. So that's going to be the beginning over here. But then at some point, you see, I'm going to start getting close to M. And if I start getting close to M, that means that my resources are going to start running out. And so that means that my population is going to have to slow down. And so I'll end up with something that looks like that. And then you can get close to the line over here. I don't know if I will be able to do that. Oh, look at that. Okay, so this is what my population will look like. It will never reach M, but it will get really, really close to it. Okay. Then if I have, yes, Matthew.
If we were to really like zoom in on the function, would it actually be smooth, or it would be like I don't know, like
it will definitely be
jagged?
Smooth.
Oh,
no,
okay.
it's definitely smooth. This is just an artifact of me not being able to be that precise.
Okay.
Yeah, we'll actually be able to find the expression for this function. Okay, so that's what we're going to do in tomorrow's lecture. We're going to start solving this type of equation.
Okay.
Okay. If the rate is a little bit smaller, the same thing is going to happen, except my initial growth will have been slower as well, right? So that just means my population is going to start growing, but a little bit slower. And then it's also going to start stalling, but a little bit slower as well, like that. And then if I have something whose rate is really large, so maybe 2 in this case, I'm going to have that my population is going to start growing very fast, but then it's also going to almost abruptly going to start slowing down. And so that means I'm going to have something maybe like that, or like you get this over here. So like, whoops. Like this. Does everybody understand this?
Mm-hmm.
All right, can I see a show of hands for everyone that understands all of this? Great. Now, here we go. The one last thing that I'm going to say before I let you try to do some problems is that if I had started at the population with a population above M, I would have ended up with something that decreases to M, right? So I said if my population is larger than M, then this rate is going to be, this term is going to be smaller than 0, and so my population would have decreased something like that. Okay, and so that would be the case for each one of them. There's a question in the chat. Yes, okay, so Galen is saying, I've watched enough coronavirus graph videos to understand. Actually, at the end of class today, I'm going to explain all of this in relation to coronavirus. So I'll just explain how we can model the spread of coronavirus using just one simple differential equation. And through our class tomorrow and possibly on Monday, we'll solve that equation and see how it relates to coronavirus right now. So I am going to make it relevant. We're going to have all the solution, the mathematical results. We'll be able to see how, like what it means to bend the curve and why people know what we have to do. But for now, we have to work our way up to this, okay? So very good, you know, connecting the dots. That's what we're going to do at the end of class today. I have questions from Radu, Galen, and Matthew. I don't know if those are hands that forgot to, okay? Galen, okay?
I have a
Matthew.
question.
Okay, good.
In the case that you did, M was, the initial point was above M.
Mm-hmm.
Does it sort of like approach M but never actually cross it? Does it stand or it crosses?
Yes, that's also just a mistake. Yeah, it approaches it. It's always, M is always going to be an asymptote.
Oh, okay, thanks.
Yeah. Right, so let me just pause the video. So what I have now is the problems from the differential equations problem set, which in which I need to model some problems using differential equations. The first one says a radioactive substance decays at a rate directly proportional to the amount present. The substance is present in the amount of 10 grams initially at time t is equal to 0, and after 2 hours, 80% of the initial substance remains. Right. So what I have is something that expresses how the substance is changing because it's decaying. So decays. When I say decay, that should bring me to the rate of change. Whoops, rate of change. And then I have a couple of amounts. Okay, so what I'm going to say is maybe the amount of the substance at time t. That's going to be my function, right? So t is going to be equal to time. Oops. And then maybe a, which would be a function of t, is the amount of substance at time t. Okay. So what I have is that the radioactive substance decays at a rate directly proportional to the amount present. So that means that the rate of change of the amount, so dA over dt, I'm going to write it like this because this is the notation that we're going to be using in general, but this is the same as writing a prime of t. This is going to be equal to so it decays at a rate proportional to the amount present. So that means it's going to be some constant times the amount present at a given time. right? Now, because it's a decay, I'm going to put a minus in front, okay? That just tells me, okay, so my amount is decreasing at a value that is proportional to the amount that there is at a given time. So I could rewrite that as minus k times a of t. Okay. Now, there's one thing that I want to note note on over here, which is that even if I didn't put the minus in front, my my equation would still be true, right? So for example, if I said this is equal to just some number, maybe c times a, this would also be right, because all that that would be saying is essentially now here, this term c would be negative itself. So that means it would include the minus within itself. Okay, so whichever way of the two you use, this is going to be right. Do I have any questions about this? No questions? Who had found something like this, like this equation for the, or like either of the two? Okay. All right, so this is the first equation, which is the differential equation, right? So you have the differential equation. And here you don't have necessarily the rate. So you're going to see that's going to happen a lot. You're going to have to find the rate yourself, but we still have to be able to formulate the equation. Then you had two possible values for this amount. So it said the initial amount is 10 grams. So that means that A at time 0 is equal to 10, right? So the amount at time 0 is equal to 10 grams. All right. And then if I look 2 hours after, so if I have A 2 hours after, that's going to be 80% of the initial amount, which means that 8 grams are left. Does everybody understand this? Can I see a show of hands for those of you who understand? Good. All right, so you can lower your hand now. For the second problem, same thing. So you have that, the rate of increase of a population P. So here they actually give you the letter. Savannah, your hand is still up. Is that because you forgot to put it down?
Wait, that's all we have to do?
Yep, that's all you had to do. I said, just model the problem. You don't have to solve it. You don't have the tools to solve it yet. You try to solve it, you're gonna like freak out. Is that what you were doing? Freaking out about it?
Yeah.
Okay, good. That's normal. That's normal. Okay, so you don't have the tools to solve any of this yet. Because it's like, okay, how do I integrate just A, just T, we don't know anything yet. Okay, you don't know anything yet. I know some of it. Yes, Galvin.
I misclicked.
Oh, you misclicked. Okay. So for the second problem, same thing. We're gonna have a population. In the population, you're given the letter. So P is the population at time T. And the rate of increase, so that means the rate at which the population is increasing. D over dP, dP over dt is proportional. So again, there's some value over here, K, to the number of, so is proportional to the product of the population size P. So it's proportional to P and to time T. Does everybody understand that?
Mm-hmm.
Yeah, so it's proportional not only to the size of the population, but also to time. Okay. Another way of writing this equation would be that the derivative of the population is equal to some constant times the value of t times p of t. Right, and here's where it becomes really, really important to know the difference between p of t and p times t. Praise and spread. Okay. Everybody understands this, yeah? So p prime of t. that's the first piece of information. Now, just for reference, you have that t equals 0, according to this, corresponds to 1950. So in 1950, the population was 1,500,000. So that means P of 0 was equal to 1,500,000. And then the population grew by 5% after 10 years. So that means that P of 10 is going to be equal to 1,500,000 times 1.05, because it's 100% plus 5% of the population. Can I see a show of hands for those of you who understand what I just did on the board? Okay, so I have Thomas, Vicente, and Varu that didn't raise their hand. Hopefully that's just because you're being lazy to raise their hand. Okay. Okay. All right, so then that would mean that over here you would have whatever this number is, that would be the second value. So these correspond to initial conditions, whereas this is your actual differential equation. Does everybody understand this? Do I have any questions? Okay, so does everybody know? So can you raise your hand if you understand what the problem requires you to do, and if you feel capable of doing this all by tomorrow? There's only 5 other problems. You just have to create the differential equation and then write the initial condition. Okay, does everybody understand what they need to do? Because I asked 2 questions. Can you raise your hand if you think you know what you need to do? Okay, that makes a bit more sense. And then I guess a lot of you have a lot of things going on, which is perfectly fine. It's important that you try a couple of them, but if you understand the concept behind it, that's like going to be a big help, because I think that the main part of this type of problem is to actually be able to solve them, formulate them. Remember last semester in Calculus 1, you were doing optimization problems. And when you were doing optimization problems, the difficulty wasn't really to solve the optimization problem, but it was to formulate the optimization problem. So this is the equivalent part in Calculus 2. The difficult part in this section is not really to solve the problem, but it is to formulate it. Okay, so you need to practice that formulation. That's why today I'm focusing just on modeling. Do I have any questions? I hear a mic going off. Daniel, Juliet, and Radu, you still have your hands up. Is that okay? All right, so I'm going to just leave that as homework, the rest of problem number 1. Tomorrow I'll start introducing like the actual heavy math for this, but for now I want to introduce just a little bit of how we are modeling just within the class COVID-19, and then we can look at you know, what it means to bend the curve and so on and so forth. Is everybody good with this? Mm-hmm. Yeah. Mm-hmm. Okay. So we're going to go over just, you know, make the class worth it, at least for a little bit, in that, you know, for now we can actually solve a problem that is going on. We can actually evaluate things to resemble what's happening in life right now. And so we're going to try to model COVID-19. Right, okay, baby model. So of course this is not perfect. It's not going to model everything that's going on, but it just gives us an idea of what all of those videos and all of that information is all about. So COVID-19 a basic model. Okay. So the idea here is that we're going to start by saying, well, here we're going to start from the perspective of the virus. Okay, so we are taking the point of view of the virus and trying to see how it can spread, how I can reach as many people as I can, because that's how I succeed in life, right? So I'm the virus, so I'm going to get as many people as I can in here. And so what I have is that I want to model the number of people that have the virus. Okay, so where did this connect? There you go. So what I want to model is N, which is going to be the number of people who have the virus. Right, so this is what I'm trying to model. Number of people. And because, you know, this is a model for real life, I don't have infinitely many people that are available to have the virus. I have a certain amount that are available to me. So that means that I have a certain number of people that could be infected. So if I'm thinking about a city, maybe Montreal or Toronto or whatever you want to model, you have that M is going to be the population of the city. We're going to assume that the universe is the city. So that means that this is all the people that could get infected. Okay, so of course you can't have more people than there are in the city that can get infected with COVID-19. So far, so good?
Mm-hmm.
Okay. Then we have that the rate at which the virus grows, or basically the rate at which is the rate at which the number of people with the virus increases is going to be proportional to a couple of things. So first, it's going to be proportional to the number of people that have the virus, right? Because if there's very few people that have the virus is not going to spread very fast. Whereas if there's a lot of people that have the virus, then chances are that the number of people that get it is going to be increasing really fast. Does everyone understand that? Mm-hmm. Yeah, because like if there's just one person, that person can only infect the people that are around them. Whereas if you have 10,000 people, then you have that those 10,000 people can then infect a bunch of other people, right? So this is going to be proportional to the number of people who have the virus, and that is the number N, right? So this is the function that I'm looking at. That's the value that I defined over here. But then the rate at which the virus grows is also going to be proportional to the number of people that don't have the virus, right? Because if there's if you have a bunch of people that have the virus, but only a few of them are left to get get infected with the virus, then it's very unlikely that there will be a lot of new infections, right? So if there's only a couple of people that are available to get the virus at the end, then the rate at which the virus is going to spread is going to be slower, not because there's not enough people that are infecting new people, but because there are not enough people to be infected. Does everybody get that? Mm-hmm. Yeah, so if there's not that many people that are left to be infected, then the rate cannot be as large. So that means that this is also going to be proportional to the number of people who do not have the virus, and so that are still available to get infected. So that's all the people in the city minus the people that have gotten the virus. Okay. And so that means that if I want to model the rate at which people are being infected by the virus, so I have that the number of people with the virus is going to increase. So the number of people, the rate of change of the number of people who have the virus, so this is the rate of change, is going to be proportional to the number of people that have the virus and the number of people that don't have the virus. Does everybody understand that? Can I see a show of hands for those of you who understand this? Now, I'm going to go back a couple of slides and you'll see that that equation is the same thing as this equation over here, except I've just called my variable something else, right? So n instead of p, but the rest is the same. The derivative of n is equal to k times n times m minus n, right? So this is exactly this model. So what I'm going to go back, I'm going to create a new case over here. So I have my equation for the model of the virus is that dn over dt is equal to k times n times m minus n. And I know that if I model this, I don't know exactly what the rate is, but if I model this, I'm going to have a maximum capacity, which is the population of my city. And then, even if I start with just one person having the virus over here at 0, if I have no people with the virus at the beginning, I'm assuming that my universe is just my city, right? So there's no people coming in or out. So I'm going to start just with one person having the virus. This is going to increase like that. Actually, let me just make it a little bit steeper. You're going to see why. Does that make sense for everybody? So this is t time, and this is the number of people that have the virus. Jesse, you have your hand up. Is that a question? Okay. All right. Now, this is what I have. This is according to time, so maybe time in days or in weeks. I'm going to have that the number of people that get infected are going to be is going to be increasing until it stabilizes at a given point. Based on this model, everybody would end up getting the virus, right? So everybody would go, like the number of infected would go to M, and that means that everybody would get the virus, and then we would be done. Of course, this is a very simple model, so this is not exactly how things are going to happen, but it's worth studying just for the sake of seeing how these things occur. Does everybody understand this?
Mm-hmm.
Okay. Now, here's where it gets interesting. I'm going to assume, again, this is a simple assumption. It is not necessarily the better assumption that you need to make, but it gives me some information about how to model this. I'm going to assume that people spend on average this amount of time at hospital, and that everybody that gets the virus has to go into the hospital. Okay? So that means the person that got infected on the first day over here is going to have to spend all the time between here and there at the hospital, right? And this day, he will be released from the hospital. Does everybody understand that?
Mm-hmm.
Then this person that got infected there is going to have to spend all of this time at the hospital, and then he will be released from hospital that day. Then the person that was infected at this point will have to spend this time in the hospital and will be released that day, and then I can keep going like this, right? So basically all that's going to happen is I'm going to get the same curve, but it's going to be shifted by the amount of time that they have to spend at the hospital. So if I look at the population that has to go into the hospital, I'm going to look at this population over here. Should be exactly the same, okay? It's just my drawing skills in this are not the best that they could be. Right, so this is just shifted by, let's say, a week if it's 1 week, or 2 weeks if it's 2 weeks, and so on and so forth. Does everybody understand that? Can I see a show of hands for those of you who understand how I've gotten this curve? So this is just when the discharges from the hospital happen. Okay, good. Now, if I look at one time, let's say I look at what happens after, I don't know, 1 week. If I look at one time, I'm going to draw. Yeah, and I'm going to draw in, let's say, green now. Let's say I'm looking at this time, and I want to know how many people there are in the hospital. There's going to be this person that is going to be released tomorrow, but there's also going to be all the people that were received in the hospital a little bit of time later. Okay, so there's going to be the difference between these two is going to be the total number of people that there will be in hospital. Does everybody understand that? Is there anybody that doesn't understand that? Please raise your hand. Okay, so the difference between these two amounts, that's going to be the total number of people that are in the hospital, right? So this height over here, this number is the number of people that are in the hospital. So this is where I'm going to place this number, so that this height is the same height that I had over here, okay? Then at this point, maybe I'm gonna do the line. And so this line over here. Then at this time, I have that the difference between the people that were in the hospital is going to be like this. And so this amount is the same thing that I'm going to have at this time over here. Oops. Okay. Then at this time, I'm going to have these many people in the hospital. So this is what I'm going to have over here. And at this time, I'm going to have these many, oops, these many people in the hospital. So that's what I'm going to have here. And then let's say if I looked at one of the earlier times, this is what I would have here. And this is what the value would be here. Does everybody see what I'm drawing?
Mm-hmm.
Yeah. So this is the number of people that are going to be in the hospital at any given time. And this looks something. Oops. Like this. I mean, you get it, nicer. Do I have any questions about this? Can I see a show of hands for those of you who understand what I just explained? Okay, great. So now this is just based on our model, right? And we're already reproducing the things that you've been looking at in the news. Now, there's been a lot of talk about what we need to do in order to stop the spread of COVID-19. And the main concept over here is that we don't necessarily have to avoid everybody from getting the virus, but the big threat of COVID-19 is that it's growing really fast. And so that our hospitals, which might have a capacity maybe at around this value, are not going to be able to accommodate all the people that will need to be in the hospital. And so that means that not everybody is going to be able to be treated, right? So that's the big challenge over here. Instead, so there's a question. Exactly, flatten the curve. So what we're going to do now is to see, based on our model, what does it mean to flatten the curve? And so that thing that everybody's saying, that they're saying, okay, like here's how we're doing the predictions, now we'll be able to find those predictions ourselves. So hopefully you'll believe them more because you'll have them for your own amusement here. So again, you have this amount and this amount over here. Oops. This is the maximum of the city. But now what we're saying is, all right, this is the city. And we have that we can't avoid the fact that there's going to be some people that are infected. We can't avoid the fact that the other people are still susceptible. But what we can do is we can play on this parameter, right? So this term over here is the rate at which the virus is spreading. And in order to play with this parameter, we can play with a couple of things. If we were talking about a population of animals, what we would do is we would cut resources, right? So we would I don't know, what do you call that? We would not give so many, like, we would not make so much food available. We would make it more difficult for females to find males and so on and so forth. And that would slow down the rate at which a population is growing. If I'm talking about a virus, the way that the virus reproduces is by people that have the virus to meet people that don't have the virus, right? And so what we're doing is that we're saying, okay, if you stay home, then the rate at which the virus spreads is going to slow down, right? So it's going to become smaller. If that rate becomes smaller, what we said is our curve that initially was like this is now going to be a little bit smooth, like the slope is not going to be as large, it's going to be flatter, right? And so that means that our curve here, even if I start with the same amount of people, is going to be a little bit, oops. Okay, you get where I'm going. This, and then like that. All right, so this is what happens if I make a smaller k. I promise I'm already done. I'm like 2 minutes. So then what I have is that if I have, okay, so this amount over here that told me how long I have to stay in the hospital, that's independent of whether the rate of spread is larger or not, right? So that line over there is still going to be the same length. And so the people here are still going to be discharged at this point. The people here are still going to be discharged 1 week or 2 weeks after, whatever that amount is. And then like that, and like that, and like that, right? If I follow these, now here, this is where the challenge is. My God. This is going to look something like that. Show of hands for those of you who understand. Good. And now here's where the big conclusion comes up. And that is that, now, again, we said the number of people that need to be at the hospital at the same time is given by the difference between these two curves, right? So over here, for example, this is the amount, and that's going to be the amount over here. This one over here, that's going to be corresponding to the value over here. This value here corresponds to the value here. And this difference corresponds to the value here. Same thing for the first couple of values over here. That corresponds like that. And everybody sees the drawing that you've been looking at in every single media outlet, which is the fact that this is going to become like that, right? And now if we look at hospital capacity, at no point during the whole spread of the virus are you going to have that the number of people that are in hospital are going to be above the number of beds that you have available in hospital. So that means that everybody that will need a bed in the hospital will get a bed, will be able to be treated. And so the effects of the virus will not be as dramatic as they could be if, for example, all of these people couldn't be treated. Does everybody understand that? Mm-hmm. Mm-hmm. Yeah. All right. Okay, well, that's kind of my lesson over here on COVID-19. This is where all of the models that you're looking at come from. We will be able to find an actual expression for each one of these curves. We will be able to find an actual smooth curve for all of these. It's also possible to model, you know, at which value specifically does the curve start being under the hospital capacity. We don't do that in this class. It's a little bit beyond the scope of that. But my objective here is just for you to see that all of those models that are being published online come from fairly simple models that have simple assumptions, but that allow us to have a very deep insight into how the virus is spreading and how we can avoid you know, dramatic effects from that virus. All right? Mm-hmm. Okay, so hopefully, I mean, this is what I like in math, modeling real life phenomena. Hopefully you'll find it interesting as well. I think this is really where things get very interesting in integral calculus, because you are able to model things from real life and predict what's going to happen in the future. And then you can play on the parameters that come up in your model so that you can either avoid or induce things to happen in the future as well. So that's just this very simple model. We're going to see other maybe more or less interesting applications, but this is one that I think is relevant for you right now, and that hopefully it will make you understand what's going on a little bit better. All right?
Mm-hmm.
Okay, so